Alrighty, so let me just make that. That's probably okay. So friction. Even when a single force applied to an object, it is usually not the only force affecting the motion. This is because of friction. Friction is a force that always acts in a direction to oppose motion. And that was something that I brought up right like day one. And oddly enough, there was one of the common mistakes from yesterday. People didn't subtract friction when they did the problems. They added. Friction is always opposite. You subtract the amount of friction, or you add a negative. Due in large part to the irregularities of the two surfaces that are in contact. You guys realize I'm teaching now, right? Right? Here's the teaching part. You sit, you learn, I teach.
Yeah, I was thinking about that sheet.
Oh, okay, I'll get back to you in a bit. Yeah. Even very smooth surfaces are bumpy when viewed with a microscope. When an object slides against another, it must either rise over the irregular bumps or else scrape off. Either way requires a force. And the force of friction between two surfaces depends on the kinds of materials and how much they are pressed together. So that's really a different version of the definition of mu. Another common mistake. Yesterday, people subtracted mu instead of subtracting the FF. Rubber and concrete, for example, produces more friction than steel against steel. That's why concrete road dividers are replacing steel rails. Now, you don't see this a whole lot anymore. Back in the 70s and early 80s, that's when this first started to happen. There are still remnants of this. If you think about country roads, gravel roads, bridges on sort of lesser secondary and third roads, you will see these kind of guardrails. Can you think of a bridge like that? Right? Usually they're really old kind of things, right? Most major highways now have these kind of dividers, and this is why. The concrete divider is wider at the bottom so that the tire of a side-swiping car rather than the steel body makes contact with it. Why is that better? Why is it better for the rubber?
Steel and steel slides.
Exactly. Steel and steel just slides right along. Hardly slows you down at all. Whereas the concrete is going to slow you down. Well, most people don't care. This is going to mess up your car, right? So, tire, yeah.
We have those new, they're just like steel cables with these metal pegs inside. I've driven it like 3 times in the last 4 months, so.
Which part of the Trans-Canada?
Probably Saskatchewan border.
Oh, over there? Yeah. I'm not familiar with that part, I don't know. What does it look like, AJ?
It's literally just a cable held up, or 2 cables, one through the middle of steel pegs that are both that wide.
Oh.
There isn't even concrete or...
And is that like opposing? Or like on the edge of
on the edge, it's like on bridges.
Oh, really?
On the side of big curve.
Maybe that's just a temporary until they get this put in. That's, yeah, that doesn't seem...
Yeah, so I wouldn't want to hit that.
Yeah, I don't think that seems overly safe. That must be a temporary thing. I don't know. I don't. One thing I will say too is you might have noticed. I know where the overpass is there when you get to Portage. You ever noticed I think they're blue, big blue sort of like barrels right there. You know what's in those, and why are they there all the time?
Water.
Or sand, right?
So that when you hit it, it's like less your impact.
Exactly. It sort of reduces it increases the amount of time, right? And those are actually going to be filled with the first one's going to be like a quarter filled, the next one's going to be half filled. It sort of like slows you down gradually. The greater friction between the rubber tire and the concrete is more effective in slowing the car than the contact between the steel body of the car with the steel rail of the other design. Are you with us there, Zane? When there's friction, an object may move at a constant velocity while force is applied to it. In this case, the friction force just balances the applied force. And what happens when friction and the applied force are balanced? Constant velocity, which could possibly be 0. The net force is 0, so there is no acceleration. For example, in figure 49, the crate will move at a constant velocity when it's pushed just hard enough to almanac friction. What do you guys have? What do you guys have? Almanac friction doesn't make sense. Are you following along?
I don't know where it is. It's like way up.
Well, it's almost like I skipped a paragraph or so there, didn't I? That's no good. Maybe I'll go back a paragraph then. I must have, when I scanned it, I guess it missed parts. Yeah. Okay, well let me read the page. I guess when I scanned it, I didn't get it all. Third paragraph, looks like. Friction is not just restricted to solids sliding over one another. Friction occurs also in liquids and gases, which are called fluids. In fact, that's an entire course if you're taking engineering in fluids. Fluid friction occurs when an object moving through a fluid pushes aside some of the fluid. Have you ever tried running a 100-meter dash through waist-deep water? The friction of liquids is appreciable, which means it's quite a bit, even at low speeds. Air resistance, the friction that acts on something moving through air, is a very common case of fluid friction. You don't notice it when walking or jogging, but you will notice it at higher speeds as it's skiing downhill or skydiving. When there's friction, like there's the part there, right? Yeah, so in this case, the friction force just balances the applied force. The net force is 0, so there is no acceleration. For example, in figure 4.9, the crate will move at constant velocity when pushed just hard enough to balance the friction. The sack will fall at a constant velocity when the air resistance balances its weight. What is this called right here? When the air resistance and the weight are equal. What was it? Terminal velocity. Right you are. There is no acceleration. It's continuing to fall at a constant rate. Excellent. Okay, so that's just sort of some quick review. There's some questions on the side there. Do I have them? I don't know. Let's see. They're clickers, but it's probably not worth it for only 2. Figure 4.6 shows only 2 forces acting in the book. Its weight and the table force and the support force of the table. Doesn't the force of friction act as well? Yes or no? What do you think?
No.
Okay, there's this picture here. There's only 2 forces acting in the book. It's weight and the support force. So there is the weight force and there's another one. Is it trying to move? Doesn't look like it. It's just sitting there, right? So your answer is, Brandon? I would say no. You're going to say no? Let's see what the fine print says here. No. Unless the book tends to slide or does slide across the table. For example, if it's pushed toward the left by another force, then friction between the book and the table will act toward the right. Friction forces occur only when an object tends to slide or is sliding. Right? It has to be moving. Or trying to move. What if it's like, here's an example. What if it's like, and this is extra, what if I lift it? How come the book doesn't slide? Is there friction?
Because you're not putting any force on the book to move.
I'm not putting enough force on?
Yeah.
Am I putting a force on, or what's actually applying the force to it? Gravity down the ramp, right? If I go higher, bigger move? This one?
You get high enough.
If I get high enough, right? It will overcome friction. So when I lift it, there is friction. No friction, right? Even though in both cases it didn't move. Trying to move. Suppose a high-flying jumbo jet cruises at a constant velocity when the thrust of its engines is a constant 80,000 mN. What do you think mN stands for? What'd you say? Micronewtons? Micro means meganewtons. Mega means thousands. That would be 80,000 newtons. What is the acceleration of the jet? Do I need the mass of the jet?
0.
Why 0, Leo? It's right there. Constant velocity. Constant velocity. Is reading important in these questions?
Yeah.
Yes, absolutely. When in doubt, read the question one more time. What is the force of air resistance on the jet in the previous question?
Yes.
Yes.
A, B, C, or D, Jeff?
A.
A? And I should probably have included a unit there, right? Yes, it would be A. Since the acceleration is 0, right, that the net force is 0, and that means that if the engines are applying 80,000 meganewtons, there is 80,000 meganewtons of friction as well. All right. Oh. Okay, so flip the page over. This is extra stuff. You don't need to know this on the test. This is just for interest because people always ask me about it.
Oh, better nails.
Plus, I'm going to show you the video. Thought you should get that earbud in. You can put a book on the table, and no matter how you place it, on its back, upright, or even balancing on a single corner, the force of the book on the table is the same. In other words, if this is a 1 kilogram book, it's pretty close. 9.8 newtons. 9.8 newtons. 9.8 newtons. Right? As long as the surface is the same, right? So if the friction force, if the frictional coefficient is some value there, that's the same, that's the same, that's the same. What am I changing? Changing the area of contact, aren't I, right?
Pressure.
Okay, so the force of the book on the table is the same. This can be checked by doing so on a bathroom step, where it'll read the same weight in all cases. Balance the book different ways in the palm of your hand. Although the force will be the same, you will notice differences in the way the book presses against your palm. This is because the area of contact is different in each case. The force per unit area is called the pressure. More precisely, pressure equals force divided by area of application, or in formula form, and no, you won't have to do this on the test, P equals FA. Now, where in the real world do we care about pressure? I can think of one that's particularly tire pressure. What do we measure it in, Nicole? What does that stand for?
Pressure square.
Pounds per square inch. Did you notice that it's pounds, which most people think of as a weight, right? But pound is actually a force. If it's not PSI, what's the other, the metric one? Cole, do you know this one? KPA. What does that stand for? What is it? Kilopascals. Give yourself a high target. What's that? Kilopascals. Right. It is the unit of pressure in the metric system. Kilo, of course, means thousands, so it's thousands of pascals. Okay. P is the pressure, A is the area against which the force acts, blah, blah, blah. Newtons per square meter, 1 Newton per square meter is a Pascal. When they talk about the barometric pressure, when they're giving you the weather, when they say the barometric pressure is like, anyone know? Anyone know what the pressure is? I think it's 101. 101.3 kilopascals, right? Barometric pressure. In the really old days, they would talk about height of a bar of mercury as well, millimeters of mercury. Okay. Someone was asking, was it you, Zane, was asking about the wide tires? I can't believe it. I can't remember. Was it you? A few days back? Many people mistakenly believe that the wider tires of drag racing vehicles produce more friction and thus more grip. Not true. But the larger area reduces only the pressure. The force of friction is independent of the contact area. Wide tires produce less pressure and narrow tires produce more pressure. The wideness of the tires actually reduces the heating and the wear, so they don't wear out as fast. Did I mention this already? Yeah. Feels like I mentioned it.
With like a thinner tire.
Like thinner between the inner wall and the other wall.
Instead of targeting like this, like that.
Yeah, that's what they're talking about. So if you got a narrow tire, if you're riding on a bike, you know those thin racing tires on bikes, right? They usually generally have high pressure. The idea is to reduce drag and friction. It's probably more drag than it is friction. But they tend to heat up really, really hot, right? And they can break down. Wider mountain bike tire usually has more grip on it, more tread, so that it can sort of dig into holes and stuff, right? The thinner ones are more for a flat surface. That's the other thing. Drag racing tires are running on a nice, perfect track, right? They're not pothole, and they're certainly not running in snow. You can calculate the pressure you exert on the ground when you're standing. One way is to moisten the bottom of your foot with water and step on a clean sheet of paper marked squares. Count the number of squares containing your footprint, divide your weight by this area, and you have the average pressure you exert on the ground while standing still on 1 foot. How will this pressure compare with the pressure when you stand on 2 feet? So 1 foot would be twice as much pressure, right? A dramatic illustration of pressure is shown in figure 412. The author applies appreciable force when he breaks the cement block with a sledgehammer. Yet his friend, who is sandwiched between 2 bags of sharp nails, is unharmed. This is because much of the force is distributed over the more than 200 nails that make contact with the body. Are you volunteering?
I would.
Oh, okay. The combined surface area of this many nail points results in a tolerable pressure that does not puncture the skin. Caution, and I am recording this, this demonstration is quite dangerous. Do not attempt it on your own. Or with a partner. No.
Why? Give me the word flame.
I am not going to do it.
All the ones that are-
Yeah?
Yeah.
It's so scary.
If you were to do it, and you're not going to, would it be wise to start simple and maybe start with like, a few nails, maybe 10, work your way up?
No.
What would be actually a better idea? Start not doing it at all, thank you. Start with lots and work your way down. Not a good idea.
How did you work your way down? Just one nail, right in the
Now, the big cement block, does it play any role, or is it just there for dramatic effect?
What?
There's like, the guy lies down and he puts the big cement block on the board on top. It's purely for dramatic effect.
What are they trying
I
to
feel
do?
like there's
They're just showing you that when you do the sledgehammer and you bust the blocks, that the guy's not going to get hurt. Which would provide more safety? A less massive block, a more massive block, or the massive block doesn't matter?
Doesn't matter.
Doesn't matter? The greater the mass of the block, the smaller the acceleration of the block of nails toward the front. So you're throwing that sledgehammer down, give me a second, Brandon. You're throwing that sledgehammer down, you're moving it really fast. The block and the board can't go very far, right? Otherwise, into the guy, right? So you need to slow that acceleration down. How do you do that? Bigger mass. Much of the force. Let me finish, man. Let me finish.
So I chucked a whole large iced tea at lunch. Welcome. I'll be like, quick,
Really.
as
You should have done a water bottle.
Much of the force wielded by the hammer goes into moving the block and breaking it. It is important that the block be massive and that it break upon impact. And again, I point out, do not try it.
So I did this, now it's, yeah.
But would you like to see it?
Yeah. Yeah.
I don't know.
Would you like to see something that was filmed in the 70s and so they have really weird fashion?
Yeah.
Of course you will.
You could find a video of them doing it like yesterday, probably. Yeah, sure. It's one.
That's how it
I don't know, that was so hard. Yeah.
Clearly it's been photoshopped from the 70s.
Yeah.
Well, they didn't show the guy's limbs later. Maybe he had like.
That's true. Who knows how he died, that guy?
What if he died right there? If he died right there.
Yeah.
He like died. Watching this, I was watching this video like very like.
Okay, now let's check.
Oh, I know.
So, I think, if I'm not mistaken, this is very similar to me with the book here, right? If a wooden block slides down an incline at a constant velocity is a important part of the word. The force of friction must be equal to A, the force perpendicular to the incline, B, the force parallel to the incline, C, the weight of the block, or D, the torque force, which has nothing to do with this? And the answer is B, right? If it's sliding down like this, right? If it's sliding down like so, then friction is going to be like that. And because it's constant velocity, it's going to be equal to it, right?
Friction.
I have a bunch of those, actually. I don't use them. Yeah. If an empty wooden crate is slid across a warehouse floor, if the crate were filled, okay, so you put a bunch of stuff in there, the coefficient of kinetic friction between the crate and the floor would C, remain the same.
By the way, you could add a physics student say this could be used for projectile motion.
It could be.
Like, I know it could be, but track, yeah.
How come the coefficient remains the same? The surfaces are the same. The mass, the weight of the body doesn't change the coefficient. It's how rough those surfaces are together. Junior, you should be listening. How rough they, so it's C. However, when you get to number 3, if you fill the same wooden crate, the force of kinetic friction between the crate and the floor would? The answer is? No, it would be B, increase. How come? Here you've got the empty box. Here you've got the filled box, okay? Here you've got a weight force. Here you've got a normal force. Here, because it's full, you've got a big giant weight force. And because mu is Ff over Fn, which is equal to the Fw, if the Fw and the Fn gets bigger, right? If the Fn gets bigger and the mu stays the same, the friction force also has to get bigger. You guys realize I'm going through these right now, right? Yeah. These questions could appear on the test. Yeah. I'm explaining now. I'm teaching. Okay, good. Yeah. Just want to make sure you understood how school works.
Right.
If you're happy with that, go ahead and now listen.
Well, I'm listening.
Okay, good. Awesome. Oh, you got number 3 right. Gotcha. I thought you meant you got 3 altogether.
Oh, no.
I apologize.
No, that's called.
A 5 Newton block, that means the weight is 5 newtons, with a surface area A is dragged across a horizontal wooden table and experiences a friction force of 2 newtons. What is the friction force acting on the 5 Newton block when the surface area is increased to twice? You increase the area, what happens to the friction force? I think I went through this already today. The answer is B, it stays the same. It stays the same. The area doesn't matter. I just talked about that. The pressure would change, but the force of friction would not. Area, the friction force doesn't depend upon the area. Remember I said?
Why not?
Remember? 2 newtons, 2 newtons.
That's the weight.
Yeah, but the surface is the same, the coefficient is the same. As long as the weight is the same, the coefficient is the same, the friction force is the same. Doesn't matter the area. Don't you shake your head at me, young man.
No, it's not like that, Mr. Bennett. Mr. Bennett, it doesn't make sense though.
You can't fight science.
Like, it's easier to push my phone like that, but not like that, because there's more rubber pushing down.
Ah, because it's a different surface. No? That feels the same way. Go back. Maybe in Brazil they don't follow the laws of science, but here we do. Okay, I'm still going here, Jeff. Still doing teaching. Which pair of quantities could be used to determine the coefficient of friction for ground on concrete? The mass and the speed of the block? No. The mass and the normal force of the block?
No.
Make moon?
No.
Friction force and speed. No, we don't need speed of the block. Friction force and normal force. That seems right. The answer is D. Friction and normal, because mu equals Ff over Fn.
Please know what answer is.
It seems like I do a lot of repeating, doesn't it? The force required to start an object sliding across a uniform horizontal surface is larger than the force required to keep the object sliding at a constant velocity. These forces are different because the force of kinetic friction is greater than static, decreases as the speed of the object relative to the surface increases, increases as the speed of the object relative to the surface increases, or because the force of kinetic friction is less than the force of static friction. And the answer is, my friends, D. D. Kinetic is less than static. And Leo, that is one reason why it's easier to push, right, as it's moving than it is to get it started. But once you get it started, right, then it's easier to push. That might come into what you were talking about there. Number 7, a 50 Newton horizontal force is needed to keep an object weighing 500 Newtons moving at a constant velocity. When you see that, you should underline it. What does constant velocity mean? All the forces are equal or balanced to 2 meters per second across the horizontal surface. The magnitude of the frictional force acting on the object is... Well, some of you know what the answer is. It's D. Many of you got it right. Why is it D? Because that's how much you have to push. If you have to push with 50 newtons and the velocity is constant, then the friction force is also 50. How many questions are there? 9? Okay, I'm just keeping an eye on the time. A 20 Newton block slides over a horizontal table. If it takes a force of 5 newtons to move the block at a constant velocity, what is the force of kinetic friction on the block? It's the same one, right? Is it not? I think it should be 5. Is it B? It is indeed B. The 20 Newton block, this is the weight force, right? That's how much is down. That is the weight force. Number 9, a 20 Newton block slides over a horizontal table. If it takes a force of 5 newtons to move the block at a constant velocity, what is the coefficient of kinetic friction? So we're looking for coefficient FF over Fn. If it takes 5 newtons of force to move it, so that means my friction force is 5. My weight force is equal to my normal force, which is 20. And 5 over 20 is B, 0.25. Oh, what did I do? B, 0.25. All of these are wonderful test questions. Absolutely wonderful test questions. Okay, so reminders. Thursday, review and cheat sheet. Friday, test. Monday, Tuesday, Milliken. Wednesday, I'll be back. You can show me what you've got for Milliken.
Okay, that's all.
See you in a week. Thank you for your attention.
Kim,